Lesson: Neural Networks and Deep Learning Fundamentals. Neural networks and deep learning are transformative technologies in artificial intelligence, particularly beneficial in optimizing supply chain operations. These technologies offer sophisticated capabilities for pattern recognition, decision-making, and predictive analytics, making them indispensable tools for professionals aiming to enhance supply chain efficiency. To leverage these technologies effectively, one must understand their core principles, practical applications, and how to implement them using actionable insights and tools. At the heart of neural networks lies the concept of mimicking the human brain's structure to process information. A neural network consists of layers of interconnected nodes, or neurons, which process input data to produce an output. Each connection has a weight that adjusts as learning proceeds, allowing the network to make accurate predictions or decisions. The utility of neural networks in the supply chain is profound, from demand forecasting to optimizing logistics and inventory management. Deep learning, a subset of machine learning, further enhances neural networks by introducing multiple hidden layers between input and output layers, enabling the processing of complex data patterns. This capability is crucial in supply chain management, where data is abundant and multifaceted. Deep learning models can analyze past sales data, market trends, and external variables to forecast demand with high precision, thereby reducing overstock and stockouts. To apply neural networks and deep learning effectively, professionals need practical tools and frameworks. TensorFlow and PyTorch are two widely used frameworks in the industry, offering comprehensive libraries for building and training neural networks. TensorFlow, developed by Google, provides flexible and efficient tools for deploying machine learning models at scale. PyTorch, known for its ease of use and dynamic computational graph, is favored for research and prototyping. These frameworks enable supply chain analysts to create models that can predict demand, optimize routing, and improve decision-making processes. The implementation of a neural network model in a supply chain context begins with data collection and pre-processing. High-quality data is essential for training effective models. For instance, historical sales data, customer demographics, and seasonal trends are gathered and cleaned to remove any inconsistencies or missing values. Data pre-processing might involve normalization, which scales data to a common range, ensuring that the model learns efficiently. Once the data is prepared, the model architecture is designed. This involves selecting the number of layers and neurons in each layer, which can significantly impact the model's performance. More layers can capture complex patterns, but may require more data and computational power. For a supply chain analyst, a balance must be struck between model complexity and computational efficiency. Training the model is the next critical step, where the model learns from the data by adjusting the weights of the connections to minimize the error in predictions. This process uses algorithms such as backpropagation, where the model iteratively refines its predictions by propagating the error backward through the network. Optimizers like atom or stochastic gradient descent are employed to enhance the training process by adjusting learning rates and improving convergence speed. Evaluating the model's performance is vital to ensure its practical applicability. Metrics such as mean squared error or accuracy can gauge how well the model predicts demand or optimizes supply chain operations. If the model's performance is suboptimal, techniques such as hyperparameter tuning and cross-validation are employed to refine it. Hyperparameter tuning involves adjusting parameters like learning rate and batch size, while cross-validation assesses the model's ability to generalize to new data. Once validated, the model is deployed to make real-time predictions. For instance, in demand forecasting, the model can analyze real-time sales data to predict future demand, enabling proactive inventory management. This predictive capability reduces costs associated with excess inventory and stockouts, improving overall supply chain efficiency. A practical example illustrating the power of neural networks in supply chains is Amazon's use of deep learning for demand forecasting and inventory management. By analyzing vast amounts of customer data, purchase patterns, and external factors, Amazon can make accurate predictions about product demand, enhancing customer satisfaction and reducing operational costs. Despite their potential, neural networks and deep learning models can face challenges like interpretability, where the decision-making process of a model is not easily understood. This is particularly important in supply chains, where explainability is crucial for trust and accountability. Techniques such as model distillation or the use of simpler surrogate models can help address this by providing insights into the model's decision-making process. Moreover, the integration of neural networks with other AI technologies, such as reinforcement learning and natural language processing, can further enhance supply chain operations. Reinforcement learning, which focuses on learning optimal actions through trial and error, can be used to optimize routing and logistics. Meanwhile, natural language processing can analyze customer feedback and social media data to gauge market trends and consumer sentiment, informing demand forecasting models. In conclusion, neural networks and deep learning offer a robust framework for enhancing supply chain operations through predictive analytics and decision-making. By leveraging practical tools like TensorFlow and PyTorch, supply chain analysts can build and deploy sophisticated models that improve efficiency and reduce costs. Through careful data pre-processing, model training, and evaluation, these technologies can be harnessed to address real-world challenges in supply chain management, ultimately leading to more informed and proactive decision-making processes.